Ugh, what happened? There we go. So, as you might be guessing from the title, we are going to be talking about how to get rid of this stupid window. There we go. About least squares, which is an incredibly important thing, because often you cannot solve things exactly like the systems of linear equations because there are some errors, but you can solve them as closely as possible, and the simplest way to formalize this is using linear least squares. So let me again first recap what we were talking about the last time, because this is just a generalization of that. So previously we talked about how to project on a 1D subspace, right? So if I have a 1D subspace and it's just like a line, right? It doesn't matter in what dimension space do I live. I can be in Rn. In every dimension of a linear space, I can have a one-dimensional subspace, which is just given by a single unit, or doesn't even have to be unit vector, just only has to be a non-zero vector A, right? So every non-zero vector generates a one-dimensional subspace. What do you think is this dot here? It's the 0, yeah, that's the origin, because in every linear space we have the origin, and the linear subspace has to pass through the origin, right? So I'm just recapitulating what we finished with the last time. We were talking about how to do projection of an arbitrary vector b. So if somebody gives me any vector b, where b is from R to n, could be R2, could be R3, could be R1 million, doesn't really matter. Now the projection onto this one-dimensional subspace, so the subspace is basically just all vectors Ta, such that T is an arbitrary scalar, right? I just multiply this vector by anything, and this is essentially the simple subspace you can get. And then the projection is this, right? I like drop the B on the subspace, and I get some other vector, which of course has to be in the subspace. So this is a vector of form Ta, right? Or maybe I could just call it B projection like this, like to this symbol that is like orthogonal projection on the subspace. And what we shown the last time is that we can write always this B like this, AAT by ATA. So this is the B orthogonal projection, and this is my projection operator. Is this going? Yeah, that works fine. Do you remember this? This is what we discussed the last time. So what is this? What is this thing here? Let's talk about it for a little bit. So A, you know, of course, A is just a column vector, right? So it's n by one column. So AT is a row vector. So this AAT is an outer product, right? So this thing is an n by n matrix, right? What is this thing down there? That's just a dot product, right? Dot product of A with A. So this is just a 1 by 1 matrix, or just a scalar, right? So this is just a scale applied to this matrix. So what I have here is, so this, I could also write it this way. I could write it as PAB, where PA is an n by n matrix, which is called a projection matrix, a projection operator. Does this sound familiar? This is what we had the last time. And I told you how you can derive this, right? It's very easy to derive. You just basically search the B orthogonal in the form of TA, because you know it has to be on the line, right? It has to be in the subspace. That's what we are looking for. We are looking for a vector in the subspace, which is an orthogonal projection of B. So because it has to be in the subspace, it must be of the form TA, right? And I'm looking for such a vector B or TA, such that, or let me give it the TA, such that if I do a dot product with B minus TA, that's this part here, right? This is B minus, if my TA is here, this would be what I get. And I want to get the t such that this vector, the b minus my TA, is exactly orthogonal to a. So I'm doing a little bit of a mess. I can also write it just like this. All right, this is what I was talking about the last time. And from this, we derive that t is ATB divided by ATA, because this has to be 0. And from this, we get this projection operator. So this completely describes how to project an arbitrary vector B on the subspace. Notice that this is a linear operator, because it's a matrix, right? And the funny property of that operator is that if I take its square, I just get back the same thing. Obviously, I could also like cube it or whatever, right? Then I would again still get the same thing. The idea being that once I have already projected on the subspace, then the projection operator has nothing left to do. It just returns me the same thing. Specifically, if I apply the projection operator on some vector C, which already is in the subspace, so it's already of the form TA, then I just have to get the same vector back, right? It has nothing to do. The only thing the projection operator does is it projects back on the subspace. So it basically discards this component orthogonal to the subspace. So in 1D, it's just like, in 1D we have just one direction orthogonal to the subspace, because in 1D we have just 2 dimensions, right? So one dimension is parameterized by the line, the other dimension is orthogonal to it. But this can easily be in 3D too, right? In 3D you have just like the subspace would be like a 3D line passing through the origin, and you can again project an arbitrary vector on it, right? I would like you to have this geometric intuition. The same thing works in million dimensions. No matter how many dimensions you have, you can still have their one-dimensional subspace, just like a line, right? And then project onto it. It's impossible to visualize in a million dimensions, but that's what it is. And today, I would like to generalize this from projecting just on one-dimensional subspace. We want to be projecting on arbitrary dimension subspaces. So this was essentially the simplest case where the subspace we were projecting on was one-dimensional. Okay? And this is what least squares are. The other way we can look at least squares is from like algebraic perspective. So look at this system of matrix equations. So let's say we need to solve the system of equations. And we already know how to do this, right, for arbitrary rectangular systems. And we know the solution exists only if the right-hand side vector is in the column space of this matrix, right? In this case, it is not true. This vector is not in the column space of this matrix, so there is no solution. Linear algebra just tells us that. End of story from the math point of view, right? As long as mathematicians are concerned, that's it. But if you are like engineers, that's not it, right? Because these values might be something you measured from nature. It could be, I don't know, some length of something, some sizes, some electric potential or whatever. And maybe the system does not have solution only because there was some small measurement noise, right? Because I have some errors there. Then I cannot find a solution because the right-hand side is not in the column span of this matrix. Solution doesn't exist. But it's only like an error. It should have, maybe it should have really existed if it wasn't for some measurement noise, right? There can be noise maybe also in the matrix, right? We know that everything we represent in the computer is not the exact number. Usually it's not the exact number. Usually there is like some numerical error. That's another possible source of noise, right? So if you have an engineering application like that, then you cannot just say, oh, I cannot solve it. Right? That wouldn't get your job done. You need to do something. And the reasonable something is to find a least square solution. If you cannot find a proper solution, if just the system just does not have a real solution that you would satisfy all these equalities there, then you can just look for x that is as close as possible to the solution, right? And what does it mean to be as close as possible? That means the solution has the property that if I multiply this matrix with this vector, I get exactly the right-hand side, right? If I cannot do that exactly, then I can be asking, what is the next best thing? Which x multiplied with this matrix gets me as close as possible to this, right? The idea being, if there was some measurement noise, the noise was probably small, right? So if I find this x that gets me as close as possible to the right-hand side after being multiplied with the matrix, then I have probably a pretty good approximation of the exact solution, which I cannot really get, assuming there is some noise in my matrix and my right-hand side. So that's the rationale for least squares. I can give you a simpler example where it might be even more instrumental. So let's assume, and I will connect these two things. So before we were talking about projection on a subspace, and now I'm talking about solving a system of linear equations. But as you will see in a little bit, that's actually the same thing. So let's talk about a projection on a 2D subspace. So let's say I'm in R3. I have my origin somewhere. And let's say I have let's make it really simple. It's fine. So this is my E1 vector. This is my E2 vector. And let's say I'm trying to solve this system. So I'm looking for alpha and beta such that I get, for example, 2, 3, 1. Right? So basically the alpha is the coordinate in E1, beta is the coordinate, so this is my E1, right? This is my E2. Alpha is the coordinate in E1, beta is the coordinate in E2. And so and here would be some E3, like a z-axis. And my right-hand side, this is some B, is somewhere like here. So you can clearly see that there is no way I could solve the system exactly, right? No matter what alpha and beta I choose, the last equation just multiplies them with 0. So there's absolutely no way how I could get 1, right? By multiplying zeros and summing together. So there's no way the system can have a solution, right? But you can probably tell me what would be the next best thing. What would be the least squares solution? What do you think? Yeah? Yeah, obviously, right? The best thing I can do in this case is this, right? In which case I get this solution. So I didn't get exactly the B, but I get the next best thing. I get the best thing I can generate in this subspace, right? Which is exactly the point of projection on a subspace. Because you could also be looking at it, here is my vector B, right? And it's not in the subspace. So the system does not have a solution. But what I can do an orthogonal projection on the subspace, and I get the closest thing to B in the subspace. The closest thing happens to be the 2, 3, 0 vector, which I can form by doing linear combinations of the basis vectors of the subspace. So that's essentially the idea. There is yet another way how you can look at it. So this is like the geometric way, if you will. There is also a calculus way. So it says, okay, so if ax equals b has no solution, then the next best thing we can do is minimize the norm of ax minus b squared. So we find x, or maybe I could write argmin. You know what is argmin? So let me explain from the beginning. So because I cannot satisfy this exactly, I can, as I said before, in words. Now I write it in a formula. I look for x such that after I multiply it with a, I get as close as possible to b. Right? Because what the norm of a difference of vectors is measuring, it's measuring how the ax vector is far away from the b vector, right? If they are exactly the same, if ax is exactly b, then I have 0, right? That's beautiful. If ax can never get exactly to b, then I can be asking what x gets me as close as possible to b. Right? Does that make sense? that's sort of like, now I'm like casting it as an optimization problem, as a minimization problem, right? So I can look at it from the point of view of calculus. So the argument just means return me the x which attains the minimum. That's the only difference between min and argmin. If I had just the min here, that would mean give me the minimal value of the objective for the optimal x. Well, I'm not so much interested in that, right? What I'm really after is what is the x that minimizes this thing? Question?
Why are we squaring?
Oh, that's an excellent question. So the question is, I will repeat it for the record, why are we squaring? We could be just doing this, right? Turns out that this does not matter, right? Because square root is a monotonic function. So the only difference between these two is that I square rooted this, right? Because square root looks like this, right? Because it's a monotonic function, doesn't matter if I'm minimizing this one or this one, right? But this one is easier to deal with. Because this ax minus, oh, actually, this is, yes, this is the norm, right? The norm, so remember, this is just the dot product of a with itself, right? And the norm is just the square root of it, obviously, right? So this is actually more complicated. Here I have to deal with the square root, right? Here I don't have to deal with the square. So yeah, it looks like here it's counterintuitive, and it's a really good question. Here it looks like this is more complicated than this. But the opposite is true, right? This is actually a more basic, a simpler expression than this one. So that's why I put there this, not rather than this. But it would be equivalent, right? The minimum is exactly the same. The x which attains that minimum is exactly the same. The value, of course, is not the same. The value here is the square root of this, obviously. So let's try to minimize this. What do we get? So this is what calculus is really good for doing, for minimizing functions, right? Because this ax, so we are searching for x, right? So this is actually a function of x, right? My ax minus b norm squared, right? X is a vector, so I can give it some arrows to make it more clear. And f is a function from Rn to R plus, right? By the plus, I mean that there must be non-negative numbers. Clearly, this cannot go below 0, right? The lowest this can go is to 0, but we are only interested in solving this when it cannot really reach 0 exactly. If it could reach 0 exactly, it means I could solve the system. I wouldn't have to bother with these squares. So f is a function which for every vector from Rn gives me some number, and I want to find where is the minimum of this function, right? So what I can do, I can first rewrite this and then differentiate, right? You probably know from calculus to find the minimum of a function is you differentiate the function, you get the gradient of the function and set it to 0. So this is exactly what I can do. It's a little bit funny because it's a multivariate function, but in this particular case, it's not that bad. So let's expand this. This will be actually very instructive. And just forgive me the arrows. I don't have the patience to write arrows everywhere. You know what are vectors and what are matrices, right? A is a matrix and x and b are vectors. So if I write it out, so you know how transposition works, right? Transposition works like this. Oops. I'm just copying this in a really awkward way. And now if I write it out, if I expand the product, I get this. Here I get minus bt ax. Here I get minus xt atb. You have to be very careful about the order because it's not commutative in general, right? btb. So like whatever comes here first has to be on the left from whatever comes in the term to the right, right? So what this is the xt ata x, and notice this. What is this? What is this thing? This thing is a row vector times some matrix times a column vector. So this thing is just a scalar, right? And scalar transposed is the same thing, right? So BTAX is exactly the same thing as BTAX, the entire thing transposed, which is XTATB, right? Which is exactly what I have here. So I can just aggregate these two things together and write that this is XTATB twice plus BTB. Is everybody happy about this? So maybe it helps to talk about the types a little more carefully. So A is a general M by N matrix, right? Typically, we will have the case when M is more than N, when it has more rows than columns. Now what ATA will be, it will be N by N matrix, right? X is an N vector and B is an M vector. Or X is an N-dimensional vector and B is M-dimensional vector, right? Otherwise, this would not be correct. Otherwise, it would not make sense, the dimensions. And you can verify that all this all works. And all these items here are just scalars. In particular, this BTB is a constant scalar. Doesn't depend on X, right? So what we have here is a quadratic term in X, because this is a scalar which depends on X quadratically. And this is a term which depends on X linearly. So the funny thing now is to compute the gradient of F. So I can write it, for example, like this. And I'm not going to go into too much details. I don't want to go crazy about the calculus, so I will just write the result. So the gradient is going to be a vector, because we have a scalar function here. And the gradient is essentially just the linear approximation of that function. It's a quadratic function in this case. So it does change from point to point, but in a very simple way. Well, let me just write the gradient. It's sort of similar if you know differentiation. Well, you probably don't. You said you don't have a lot of calculus. But it's similar to differentiating just univariate functions. Anyway, the result is this, 2ATA(x). It's actually relatively simple, minus 2ATB. So what happened in the differentiation was that the constant scalar, of course, doesn't matter in the differentiation because it's just a constant, right? This x is just a linear term, so it disappears in the differentiation. And this quadratic term reduced to just a linear term, right? It's the same thing as if I have x squared and I compute the derivative of a squared, I get 2x. Right, so from a quadratic term, I get to a linear term. But I mean, you could easily prove this by writing out in coordinates and then performing the differentiation. But this is not my point here. This is not a calculus class. My point is to show you that this is the condition for the x to be a minimum of that function. Calculus would normally give you just a local minimum, but in this particular case, it actually happens to be a global minimum as well. So what you know from calculus is that the minimum is when this expression, when the gradient is 0, right? It's essentially what the gradient tells you, how in which direction, what the direction of the maximum growth of the function. If that's 0, it means you are at a critical point. In this case, the critical point is a minimum. Of course, I can just divide by 2, right? That doesn't matter. So I have ATA(x) minus ATB is 0. And I can write this as ATA(x) equals ATB. This is a very important expression because it tells us how to compute the least square solution x. It's such an important expression that I will show you a different way to derive this expression purely from algebra. So this is like the calculus way to look at this problem, and there is also like a pure algebra way to look at that problem. I sort of like this optimization approach better, but it's just like a little bit complicated that you have to go through the differentiation. So there is a purely linear algebra perspective. And actually you can sort of see it from here, right? Because this, how would I call this vector? I can just call it AX, right? So in this example, remember we were looking for a point in this two-dimensional subspace spanned by the vectors E1 and E2, which gets as close as possible to B, right? It's really the same thing as as doing this, right? I want you to see the connection here. So the AX is just arbitrary point in the column span of E1 and E2, right? Arbitrary point in this two-dimensional subspace, right? And I'm looking for this point AX, which gets as close as possible it can to B, right? To this vector, or you can look at it in terms of points. I'm looking for a point in this two-dimensional subspace, which is of course infinite, which gets as close as possible to this point, which is specified by the B vector, right? I'm repeating it because I want you to remember that. So the other way the one way I can find it is shown here, and the other way is algebraic. I can say that I want my AX minus B to be orthogonal to both E1 and also E2, right? Because here, look at this. This is essentially the generalization of the projection on the 1D subspace, right? And I said that the projection, it was here. The projection is such that the angle here is the right angle, right? That I like drop it on my subspace orthogonally, right? So here is the same thing. If the AX is as close as possible to B, then the difference between them, the difference between AX and B, must be orthogonal to my subspace spanned by E1 and E2. Which means that the vector AX minus B has to be orthogonal to both E1 and E2. The idea being that if I move a little bit away from that, I get only something that's like further away from B, right? This is the closest possible thing. So this here is my subspace, and here I'm orthogonal to the subspace. If I was not orthogonal to the subspace, I'm only increasing the distance between my point and B. That's the geometric or linear algebraic way of coming to the same thing. Here I will show you how you get ultimately to the same equation. So here is the same thing in text. So here I call it the error vector. So this thing here is my error vector E. E equals B minus AX, or AX minus B, the sign doesn't really matter. And what we want from this vector is to be perpendicular to the column span of A. That's the subspace where I'm allowed to be, right? That's the subspace generated by all vectors AX. So that means that E has to be perpendicular to all the columns of A, which I can write this way, right? So E is orthogonal to every column of A. If I write A like A1 is the first column, A2 is the second column, and so on, and I have n columns, so A is again M by N matrix. And I can write it also as A transpose E, this should be bold, right, because it's a vector, is 0, right? And now look at it. E is AX minus B, right? So if I substitute the AX minus B, I take this, plug it in here, then I get AT AX minus B. I get this formula. This has to be 0. And this is exactly the same thing I derived previously using calculus, right? This is just ATAX minus ATB equals 0, or ATAX equals ATB. So this is I think this is called normal equations, and this is the key to linear least squares. And geometrically, the solution is just the orthogonal projection of the vector B on the span A, as I was showing before on that example. And really, you can compare here, ATAX equals ATB, it's the same thing. Got it? By the way, there is an informal way, if you want to say like that my least squares, so this is like not automatically correct, but it's good to remember it, right? So this is my m by n matrix, and this is an n by 1 vector, and this is m by 1 vector. So if this is like, this equation is not exactly equation, the equation cannot be satisfied, so I like sort of relax it to a least square solution, that's what these waves mean. Then I can turn it into a least square solution simply by multiplying this entire thing from the left by AT. And if I plug this AT here, so AT here and AT here, then I can write their equation. That's like the way you can remember it. But the way it's really like derived is either geometrically this way, or using calculus by minimizing a function. Okay, now we still need to solve this, right? We still need to solve this system of equations. Now it's sort of nicer because ATA, what is the dimension of ATA? So A is m by n, right? So ATA is what size matrix? N by n. So it's a square matrix, right? That's one very nice thing. So next I want to show how to actually solve it and show that this always does have a solution. It'd be sort of weird if it didn't have a solution, but it's good to think about the reason why, right? It always has to have a solution. It may not have to have a unique solution, but it always has to have at least one solution. Otherwise it wouldn't really be useful, right? So let's look at this matrix ATA. The ATA is, by the way, a super important matrix. It's so important that it sometimes has a name. Some people call it like Gramian matrix or covariance matrix. You don't have to remember that name, just remember that the ATA is really important. Like typically when you are dealing with a rectangular matrix, at some point you will do ATA or AAT. It's the same idea, but ATA is not the same thing as AAT, obviously, right? What is the dimension of AAT? M by m. So it's even different dimension, right? So it's a completely different thing. So don't confuse the two. So the first thing to notice is that ATA is square, and it's symmetric. That's another cool thing. So symmetric matrices are those that after transposition I get the same thing, right? So why it's true about ATA? Well, let me transpose ATA, right? So ATA means, so first I'm transposing, so you remember if I have AB transpose, it gives me BTAT, right? So let me apply this rule here, where this is the first matrix and this is the second matrix. So I first transpose AT, right? And then AT transpose twice. But transpose twice just gives me the same thing back. So really ATA transpose is just ATA. So it is a symmetric matrix. Everybody agrees? Good. So it's a square and symmetric, which is very nice. You will learn to appreciate this property, especially later when we will be talking about eigenvectors and eigenvalues. And one key property of ATA is this fact, that the null space of ATA is exactly the same as the null space of A. That these matrices are intimately related. So I can write it like as like a theorem or lemma, that the null space of ATA is exactly equivalent to the null space of A. So how do we prove this? So we have to show two implications, right? First, if I have something in the null space of A, it better be in the null space of ATA, right? And second, the other way around. If something is in the null space of ATA, well, it must be in the null space of A. That's what means. These are sets. These are actually subspaces, but this would work for arbitrary sets. And I'm just showing that the two sets are equivalent. So let's do the first implication. So if I have something in NA, if I have an X, like start like this. If I have X in NA, oh, it's actually done. Then that means that AX is 0, right? That's how the null space is defined. But if I multiply this by AT from the left, that means ATAX is AT0. AT0, of course, has to be 0, right? So that means that ATAX is also 0. But that means that X is in the null space of ATA, right? That was the simple implication. So it's obvious that if something is in the null space of A, it's actually written here, then it's also in the null space of ATA, right? So that's one implication. That sort of tells us that NA is a subset of an ATA. Now we need to show that the opposite inclusion is also true. That's a little more tricky, but not super tricky. So what do I need to show here is if I take something from ATA, I need to show that it will be in A. So if I maybe here from here, if I have a vector in the null space of ATA, then it's in the null space of A. So let's see. So if something is in the null space of ATA, that means that if that's something I will call Y, that it means that ATA Y is 0, right? So let me now dot product it from the left with AT, or with Y. So if this was 0, then clearly after multiplying this with transpose of Y, it still has to be 0, right? So it means that YT ATA Y is 0. But what is YT ATA Y? So I can rewrite this. So the first part here, that becomes just AY transposed, right? Because YT AT, I can also write it as AY transposed. That's again just this transposition rule. Transposition and multiplication, right? And AY transpose AY is just the square norm of AY, right? This is just some vector. AY is just some vector. It's supposed just like the XT X is just the square norm of X, right? And because we know that this is 0, that means that this also is 0, that the square norm of AY squared is 0. But there is only one vector whose square norm is 0. It's the 0 vector. That means that AY has to be 0, right? If AY was not 0, if it had somewhere some small epsilon thing, then there is no way the square norm could be 0, right? So it really has to be 0. So that shows the opposite implication, or it shows that the null space of ATA is in NA. So from this we can conclude, because we have these two inclusions, that really ATA equals NA. So this property will have a number of important consequences for linear least squares. One of them is that you can now purely algebraically prove that this system, ATAX equals ATB, always has a solution. I just want to make some space here because I don't want to go away from this yet. So how do I prove, just purely algebraically, that this always has a solution? So that means that I need to prove that the column space of ATA is exactly the same as the column space of AT, in other words, the row space of A, right? In other words, any time I get something in the column space of AT, I can also generate it from the column space of ATA. This means that this always will have a solution, right? Now let's so we know that these two are equal, and what we discussed previously is that the orthogonal complement of a null space, the orthogonal complement of the null space is the column space. The row space, the column space of that thing transposed. But in this case, this is a symmetric matrix, right? So in this case, it's just the same thing. Now the null space of A, the orthogonal complement of the null space is the row space, or CAT, right? This is what we discussed when we were talking about the 4 fundamental subspaces of an arbitrary rectangular matrix. But the orthogonal complement of the null space is the row space. And here I just applied it to matrix A, and here I applied it to matrix ATA. But the null space of A is the same as the null space of ATA. That's what we have just proven, right? So this is a corollary of that. So because the null spaces are the same, then obviously their orthogonal complements also have to be the same, which means that CAT is the same subspace as ATA. And that proves that this system always has at least one solution. All right, so we are close to finding it. So how do we find it? Can find it using pseudo inverse. I was sort of like mentioning pseudo inverse previously. Here is finally what it is. So if I assume that my matrix has full column rank, that the rank of A is full is n, the maximum rank it can have, then because the null spaces of A and ATA are the same, then so the full rank means that the null space is dimension 0, right? Remember the formula from the 4 fundamental subspaces. Then the dimension of the null space of ATA also is 0. That means that it has to have full rank 2. It has rank n, right? And if a square matrix has full rank, it is invertible. In which case, we can simply solve, so what we get, the normal equations look like this. And if it's invertible, then I can just invert this thing, and I have my solution. And this matrix, ATA inverse AT, is called the pseudo inverse of A. Because A was a rectangular matrix. A looked like this. So I cannot talk about inversion because it's not a square matrix. But what I can define is pseudo inverse, which is the next best thing to inverse matrix. So what is the dimension? If my dimension of A was m by n, let's see. So this is n by n, right? And AT will be n by m. So the pseudo inverse has dimensions n by m. It's like the transpose of A. So the pseudo inverse is the next best thing to inverse if you cannot do inverse because the matrix is not square. So let's look at some simple examples of these squares. These squares are super useful. So here is like a very basic, very simple example. So let's imagine I give you, if I'm an R2 and I have a bunch of measurements, bunch of points, x1, x2, x3, arbitrarily distributed, it doesn't matter, x5, and I have some y values for each of them. So this would be like y1, right? Here I would have y2, and so on, right? So I have some number of points here. So those are my data samples, x, y, y, I. So here I have 5 data samples, and I want to fit the line which best approximates all these points. So I want to solve for coefficients m and x such that this line ideally passes through the points, right? Because not all points lie on the same line. If I have 5 points, there is no reason why they should be lying on the same line. Can happen, but generally does not have to happen. Then I will just say that I want to solve this in the least squares sense. That I want to find these unknown m and c parameters. So m and c are just real numbers. And I have to find them that the line defined by m and c, so the line which is just f x equals mx plus c, will be as close as possible to passing through these points, right? So I'm to find a line that looks something like this, right? Not a line that's like crazy somewhere else, but a line that if the points were exactly on one line, that would be the solution, right? And this is a typical example of a problem I can solve with linear least squares, because all I need to do is put all these points in a matrix xn if I have n points. Then I say here are my unknowns m and c, and here I say this has to approximate my y's. So I know the x's, I know the y's. The only thing I don't know is this, right? So this is my a, this is my x, and this is my b. This is exactly the first problem, right? And now you know how to solve it. The solution is just ATA inverse ATB. And this is a 2x1 vector, and from this you get the m and c. You can plot the line, and it better be pretty close to the points. Okay, I will need to finish unless you have some questions. Yeah? Oh, yeah, that's a good point. It's, yeah, I guess the terminology, if A is a homogeneous matrix, well, not really, right? Homogeneous matrix would have to have zeros here and 0 here. But this doesn't matter, right? It's just the matrix which realizes the fact that these points are the line equation, right? The point of this matrix is to do this mx1 plus c, right? So I guess the trick is really similar to homogeneous coordinates, yeah. Any other questions? All right, if not, then I will not see you on Friday, but I'll see you on Monday. Okay.